So, as our first speaker, we are very happy to have Dmitry Talalaev, who will tell us about a family of the Poisson brackets on GLN compatible with the Sklyanin bracket. So, please.
Thank you very much. And firstly, I'd like to thank the organizers and all the participants. It's my first time in BIMSA, and I find the atmosphere really exceptional from the working point of view and from the humanistic point of view. So thank you very much. The subject of my talk is written, but it's only part of a big program concerning the study of the full Todo system, and you will see many objects and many construction during my talk, which are related with the subject of previous talks, with cluster algebras, with quantum groups, and many others. So for me, the full Todo system is very interesting due to its algebraic and geometrical structure, which is very rich structure for me personally. This talk is principally based on our recent paper, joint paper with Volodya Sokolov. It was just an exercise we have done, but the structure we have found is really interesting for us. So the principal object is a family of compatible quadratic Poisson brackets on GLN. Which include the Sklyanin 1 and generalize it. And it satisfies a characteristic property. All anti-diagonal minors of the Lax operator have log canonical Poisson bracket with all generators. So it is even more powerful condition than in the talk of Professor Liu. But it's like this. So we impose this condition. We also consider the compatible linear bracket compatible with the quadratic one, which is defined by the argument shift method from the quadratic bracket, and we examine the by Hamiltonian formalism for some pencils in this family of quadratic brackets as a method for construction in involutive families, involutive subalgebras related to integrable system. And I will try to provide you some interesting examples of families of this type, and we'll try to explain the relations with more algebraic questions of invariance in very different contexts. Okay, that's the explanation of my last idea. So I will explain how to produce some centers of Lie algebras and the centers of Poisson brackets in terms of anti-diagonal principal minors of the Lax operator. I will start by introducing some notations which are quite standard, but I will try. So I can see just the vector space Cn, Eij are matrix units. Small Eij are generators of the Lie algebra GLN. Just the most natural Lax operator is this matrix, and here are its tensor copies of this Lax operator. The main family of quadratic Poisson brackets is of this type, the formula 1, I will call it 4-term quadratic Poisson bracket. This particular example appeared in talk of Lunia. So the Sklyanin bracket is of this type, and both all the examples of this type appeared in the quantum inverse scattering method. The Sklyanin one has its fundamental role in describing the Poisson groups, and the 4-term quadratic Poisson bracket appeared in works of Semyon Vitenchansky, Maillet, Teher, Souris, starting from the 80s. One of the geometric description of the 4-term R matrix bracket was an interpretation of this bracket in terms of the standard R matrix bracket on the double of GLN. It was, if I remember well, in the work of Semyon Vitenchansky and Alexey Sevastyanov. There is some natural condition of normalization for the components of this 4-term Poisson bracket. So I'd like to say some words about the quantum part of this bracket, and as I mentioned, they appeared in the framework of the quantum inverse scattering method, and the good quantum object are RTT algebras and reflection equation algebras, and I will recall what is it in few details. So first of all, I'd like to recall you the famous R matrix, which is due to many others, the one Cherednik, Drinfeld, Jimbo, and I suppose some others. This is a matrix of this type. It is a solution of the Yang-Baxter equation and the core object in many structures of quantum integrable systems. An RTT algebra is defined as a quotient algebra or the free tensor algebra of generators Tij, small Tij, subject to the quadratic relation RTT. So I use here the standard notations for the matrix, for the generating matrix T and its tensor copies. Reflection equation algebra were first appeared in the work of Cherednik of 1984 in the study of scattering processes with a boundary. Such an algebra is also defined as the quotient algebra of a free tensor algebra by quadratic relation, but of the different form. So this is an equation which defines the reflection equation algebra. I use also the same standard notation for the generating matrix. These algebras are related with the quadratic Poisson structure by the known procedure of classical limit. I'd like to recall you this construction. So the R matrix can be expanded in the parameter H bar. I introduce such matrices as the coefficients of this expansion. Where P is just the transposition. And I also introduce a matrix R, small r, which is the product of these matrices, and which has such form. So if we do just the classical limit h to 1, the RTT algebra produces the Sklyanin bracket. I introduce another notation. So a star is an involution, which is just a conjugation by the permutation. it acts like this on decomposable elements. And if you introduce also R star, then the limit procedure, then starting from the reflection equation algebra, produces a 4-term Poisson bracket. I suppose that it is the same as in the Leonid Chekhov talk just before.
Excuse me.
Yeah.
Capital P.
Sorry.
Is capital P is a standard matrix, the project plus to minus. Is that correct?
No, P is just a
Oh, it's
transposition.
there. I'm sorry,
Yeah.
I didn't see that.
It is just a transposition,
Okay, thank you.
like this. Another classical construction, which I'd like to recall you, it is called the argument shift method, and it makes a relation between the quadratic Poisson bracket and linear ones. If we have a quadratic Poisson bracket, we can consider just the change of coordinates, like to pass from the coordinate L to the matrix elements of this matrix L. It's a game. Okay, matrix element of L plus lambda E. In the new coordinates, the initial quadratic bracket can be expanded on the parameter lambda. It has 3 terms. The first term is just the initial quadratic bracket. The coefficient at lambda is a linear quadratic bracket on the coefficients of the Lax operator, and at lambda square we have the constant operation. The linear term has can be expressed by such a formula. If we suppose such a condition on the coefficients of the 4-term quadratic Poisson bracket, then this term vanishes, and just this construction produces the pencil of compatible Poisson bracket. Just this construction shows that the linear operation is a Poisson bracket. Yes, so just this condition guarantees the Jacobian identity for the linear part of this expression. If we just consider the linear bracket, which is given by this argument shift method, if one starts by the classical limit of the reflection equation algebra, we get the standard JLN Kirillov plus constant linear bracket on the coefficients of the Lax operator. Okay. So the main hero of my talk is the family of quadratic brackets of this form. They are of the form 4-term quadratic bracket like this. Their matrices A, B, and S are of this type. So just for better understand the role of elements, the matrix A, it controls this part with W, controls the Sklyanin bracket. But we have an additional term here. All other terms are diagonal. But there are many constants which play the same role, the same game. So for each set of these constants, this 4-term this 4-term Poisson bracket is a Poisson bracket. So there is a quite big family of 4-term quadratic Poisson bracket of this type. The linear bracket for this system, for this family of quadratic brackets, is given by this formula. Just some notations which is obtained. You see the parameters. The parameters in this formula are the coefficients. A, but these are whole matrices of parameters A, B, and S. So with the help of these parameters, I introduce some new coefficients which are helpful to describe the linear bracket compatible with the quadratic one. So this linear bracket, if we restrict it to the nilpotent part of generators of the Lax operator, they coincide just with the standard Kirillov constant bracket on the nilpotent part multiplied by constants to w and minus 2w respectively. The nilpotent part commute between themselves with respect to the linear bracket, but the action of the Cartan subspace on the nilpotent parts is not trivial. It is given by these formulas. So you see, here the parameter h are expressed in terms of the coefficient a, b, and s from the definition of this family. So this structure is quite simple, but it is not trivial, and there are important examples of this type. So this is the linear part, the linear bracket compatible with the quadratic one, and the next ingredient of my talk is some set of functions which are antidiagonal minors of the Lax operator. They appear in many different contexts. Initially, for me, was their role in describing the integrability of the full Tode system, but they appear as cluster coordinates. Their role is very geometric and important. So they appear in describing the cluster structure of Lecq varieties, for example. And both issues, I'd like to say that their role in full Tode system and in cluster varieties could be quantized. Has natural quantization. So my notation are the following ones. So delta k plus and delta k minus are upper and respectively lower left antidiagonal minors of my Lax operator of size k. And the following property is characteristic for the family of quadratic brackets. So for all quadratic brackets of this family, all the Poisson brackets of these antidiagonal minors of both families are log canonical. And obviously give an intention to construct important objects in terms of some monomial expressions of these antidiagonal minors. They are functionally independent, and it gives hope to construct some full involutive families in some interesting contexts. Okay. Now I will consider just more special subfamily of the quadratic brackets of this type. They're written by this formula. Just for better understand the rules of this element, this part is the Sklyanin one, is the Sklyanin bracket, and there are some additional diagonal or just log canonical part in terms of the generators. So we add to this Sklyanin bracket just a log canonical bracket in terms of the genuine generators of this Poisson algebra. All such brackets are of our type. I will give just some examples of these brackets for this choice of parameters z1 equal to 1 and other parameters trivial. This bracket is just the Sklyanin one. This choice is also interesting. Another one. This one. I will comment on such examples a little bit later. The linear bracket in this type, in this specialization, four-dimensional specialization of our compatible family of quadratic brackets is described by these formulas. So the nilpotent part always commute, and the linear bracket restricted to the nilpotent part is just the standard Kirillov-Kostin bracket on these subspaces, but the action of the Cartan subspace is given by these formulas. There is another important choice of parameters, this one. In this case, the linear bracket is just the bracket on this decomposition with the commuting factors and the minus bracket on B minus. So such a bracket is given just by the R matrix form. The R is a difference of the projection of the projectors corresponding to factors of this decomposition. Next topic is related with the centers of the quadratic brackets. It is natural to try to find the centers in terms of the monomial of antidiagonal minors. And I will. The first example is the description of the center for the Sklyanin bracket. It is given like this by the ratios of such minors. Very close result was obtained by Fok and Marshakov in 1997, by Lenichekov and Martmazoko in 2010. But these general properties of log canonical brackets of antidiagonal minors produces interesting description in other cases. For example, in the case which is related to the decomposition of B plus and N minus, we can construct central elements in terms of such monomial expressions. So the theorem states that such ratios and products of antidiagonal minors produces a center of this Poisson algebra. There are some more exotic examples and explicit construction of centers in these cases. For example, if you choose such values of the parameters, then such strange family of monomials in antidiagonal minors belong to the center. So this case was interesting for us due to the property that in this case, there is some Poisson reduction procedure which produces what is called the full constant order system. So some other examples of constants and central elements. This one, another exotic example, but it is also interesting because in this case, there is a Poisson reduction which produces a Hamiltonian structure for the standard three-diagonal open-order chain. Just remark that some parameters Z3 it doesn't influence the linear bracket, but amazingly it is responsible for the Poisson reduction, which produces some versions of the Toda system. For the moment, it's a hypothesis, but we hope that all families of functions listed in the remarks and theorem before, they produces the complete description of the centers, so they are full set of generators for the centers. For smaller n, we have verified this, but for the moment it's a hypothesis. Okay. Due to the relation between the quadratic Poisson bracket and the linear one, which is given by the argument shift method, it is interesting to follow how our generators of the center survive in this limit. And I'd like to recall you also some folklore theorem, but maybe it's better to make a reference to the work of Magri. So let CL be an element in the center of the quadratic Poisson bracket. And this Poisson bracket, after the shift of argument, produce a pencil of two brackets of quadratic and linear one. Then this function lies in the center of the generic Poisson bracket in this family. And the simple lemma shows that if this function is a polynomial, then all the coefficients of the series are commutative functions. And moreover, and they are commutative with respect to both, to complete pencil of Poisson brackets. And moreover, the highest terms of these expressions produce the center of the linear bracket. Some refinement of the statement. Not only the highest element of this expansion is central, but we can say that the highest non-trivial, non-constant coefficient lie in the central, will be important in what follows. And surely we can consider the family of central element and the expansions and all the coefficients of expansions of entire family of central elements. Okay, I will provide some application of this lemma in some simple cases. And the first one is the case corresponding to such a choice of parameters, and algebraically it corresponds to the direct decomposition of our Lie algebra as a direct sum of Lie subalgebras, but here they are ideals. if you remember, in this case, the center of the quadratic bracket is produced by two types of functions of the ratios of such minors and the product of this one. I expand both on the parameter lambda after the shift of arguments. Here the principal coefficient is 1, so it is constant. So the important coefficient here is the subdominant term. And in the product part, in this family, the non-trivial coefficient is the dominant one. It is the square of some antidiagonal minor. So both statement, the description of the center in this case, and the shift of argument lemma, Magri lemma, shows that that both functions, both families of functions, these coefficients and this one, they belong to the center of the linear bracket. So just to the linear bracket, which is the restructure of this direct sum. Exactly. Yes. In particular, the coefficients of the characteristic polynomial of the Lax operator in this case lie in this family. In the Sklyanin case, the center, these ratios are in the center, and after the shift of arguments, we obtain such an expression. So I'd like to choose the dominant and subdominant terms, and the lemma shows that these ratios and the expression of this type belong to the center of the linear bracket corresponding to the Sklyanin one, to the Sklyanin quadratic one. The proof is just trivial. So this part is given by a very simple argument, but to obtain this, we have to consider just the product of this series and to take the first non-trivial term, which is subdominant, and it is given by this formula. And I'd like to make some relation of this method with some different method in integrable system, which is called Giffen-Zeitlin method, which produces involutive algebras from some towers of subalgebras. I will explain. So, but first of all, it was important in our study due to the method of constructing the integrals of the full-order system, which is due to Dave and his colleagues, else from the HS, from the 86. I'd like to consider the family of nested Lie subalgebras. They are denoted by Gn with upper index K, and the subalgebras are formed by the upper right corner of the Lax operator. So just all elements of the Lax operator in the upper right corner, they constitute a Lie subalgebra, and the method of Giffen-Zeitlin is to consider the algebra generated by the centers of all Lie algebras or all Poisson algebras in this tower. So I will look on this, and I'd like to compare this construction with the result shown in the beginning. Okay. Let's consider upper triangular antidiagonal minors, and the minors after the shift of argument. So the function depending on lambda defined by this formula. So there is a theorem that coefficient of such partial characteristic polynomial of the Lax operator lie in the center of this partial Poisson subalgebras. So I consider the Poisson subalgebras corresponding to these Lie algebras. So I have a tower of Lie algebras and the corresponding tower of Poisson algebras. And moreover, I prefer to consider the tower of field of fraction of these Poisson algebras because normally I work with the rational functions with some ratios of antidiagonal minors. So this the coefficients of these expressions lie in the centers of these Poisson algebras. Yeah.
How trivial is this theorem?
It's very simple. I'd like to say that it's simple, but it demands some calculation. But linear algebras, just with matrices. I'm sorry. So just considering this, I couldn't say that it is new, but I could give you a reference now. I hope that it is not new. Okay, but so this element produces the centers, and all the algebra generated by all elements of these coefficients. It is a commutative family with respect to the standard Kirillov constant bracket. So it's the origin of many integrable systems. Moreover, these coefficients, so there is a strong statement that these functions are invariant with respect to the uptriangular nilpotent subalgebra. So not only of these subalgebras, of this subalgebra. Both is true, but what is more important for me is that the coefficients are invariant with the action of the nilpotent group. And both such statements give a lemma that just the upper right antidiagonal minors with these numbers restricted by the half of n belong to the center of the nilpotent Lisa algebra, and it's Poisson algebra too. So it is simple. So it's like in the centralizer, but such minors are else the element of the algebra itself. So they are central due to this coincidence. So this demonstration is also simple. Which is a little bit more delicate is the description of the center of the Poisson algebra, which is the field of fraction of the Borel subalgebra. And it is given by this similar construction, so we also consider such a partial characteristic polynomials of Lax operator. And the statement is the following, that the ratio of two first coefficients in this expansion lie in the center of this field of fraction. So the fact that they lie in the centralizer is due to the previous statement, but exactly this ratio lies in this Poisson algebra itself. So it is a central limit. And the last remark that this this ratio is exactly the delta k star I introduced before using this argument shift method, starting from description of the center of the quadratic algebra. I will return to this page. Yeah, here. So you see, one of the choices of our quadratic Poisson algebra was this one. Its corresponding linear Poisson bracket was the same as the Kirillov constant bracket defined by this direct decomposition. From the quadratic algebra, we have such a description of the center. And these coefficients correspond exactly to the central element in the field of fraction of the Barrel subalgebra. So the approaches coincide. It was important for me for some reasons. Okay. Yes. And it is principally the end of my talk. So I'd like just to recall the principal things that in some sense the initial point of our exercise was the characteristic property of our family of compatible Poisson structures. And this property was the condition that some minors, the antidiagonal minors, have log canonical Poisson bracket with all the generators. It was important in our work, but I couldn't say yet that it is well understood. So we hope that it has some geometrical interpretation and some geometrical generalization related to factorization problems, Manin triples, and etc. And we also hope in future researches to understand its quantum counterpart, consisting the quantization of this family of compatible Poisson structures, of centers, commutative families, and absolutely the relation of the quadratic and the linear part too. Thank you very much.
Thank you very much. Questions to the speaker?
Can you turn to page 15?
50?
Yeah, so what's the bi-Hamiltonian structure of cosine tilde that you're talking about? Like 15.
It is not written here. It is not written here, but it is.
Right. Can you briefly?
Yes, we can discuss it.
Oh, okay. And also you mentioned like their connection with when you begin your talk, you mentioned their connection with cluster algebra. I mean, these principal minors and log canonical relation, of course, like they are related, but can you see a little more? For example, like where is the role of mutation relation? Like.
No, not mutation relation, but it is principally related with the flag variety, because the full Toda system can be described on the cells of the flag variety.
Okay.
So.
Okay. Thank you.
Okay. Questions?
Dima, my question is related to the previous one because there is this activity by Gehman, Shapiro, and Weinstein So they use minors to define actually cluster variables.
Yeah.
Well, not only principal minors. So there are some. Is it somehow related to what you have here?
I hope so.
Hi, my question regarding that matrix structure and related to integral systems. So you see, you have a Poisson algebra.
Yeah.
Okay, you give us the example. The total lattice would be one of the special examples in integral systems. Do you have other new integral systems included here? For example, did you have Lux pair for those integral systems?
So, thank you for the question. It was, in fact, it was motivating for this work. We started to
Yeah,
analyze
because I saw you list the Sklyanin bracket.
Yeah.
Yeah.
I'd like to return to the beginning, to the form of the Poisson bracket.
Sure.
There is a Lux operator and the Poisson bracket, and exactly we started to find a Poisson bracket for the Toda system, which is a very important example of integrable system. And we failed to find it in the Sklyanin form. So we started to... No, the complete Toda system, the full Toda system, and not only the symmetric one, but it's lived to the whole GLM.
I see.
And it failed to be to have a Poisson structure of the Sklyanin form.
Yeah, because in integrable system, the total lattice is kind of a discrete version of the...
No, it's not the lattice. It's a
It's not the
generalization
lattice.
of the chain, of the
Toda
Toda chain.
Okay.
But the generalization to the full symmetric matrices, and moreover to the full GLM. So for us, the choice of the Poisson structure was not auxiliary. It was by necessity. There are no other Poisson brackets.
I see.
We have to consider such Poisson brackets.
Oh, okay, it's not a standard one.
Yeah.
Okay, thank you.
It is standard, but it is related not to the RTT algebra, but to reflection equation algebra.
Okay. All right.
Okay, more questions? If not, let's thank the speaker again.